Hello and welcome to your second review video. I've got a couple pages of notes I want to go over. Today's topic is derivative and integral rules. And then after that I have a couple of AP free response questions I want to go over with you. So if you want to call this AP Review Day 2. You can call this derivative and integral rules. Okay, so I know that you don't really have to memorize these so much this year, especially since it's all open notes. But if you have these written down, there's some general rules. I'm not going to write all of them. I'm not going to do all the trig rules and stuff like that, but know what they're called. If I say the power rule, what is the power rule for derivatives? That's the one you probably are most familiar with. That's just the derivative of x to the n power is equal to n times x to the n minus 1 power. You do that all the time. Product rule. It's important that you know this in terms of its formula in addition to how to do it. So the derivative of f of x times g of x is the first, which would be f of x, times the derivative of the second, g prime of x, plus the second, g of x, times the derivative of the first, f prime of x. And I know some of you might do this in a different order, but since it's multiplication and addition, it's all commutative, it should be fine. Quotient rule. If I asked for the derivative of f of x divided by g of x, I've been doing a lot of L'Hopital lately, so don't confuse it with that. It's not just derivative of the top and derivative of the bottom. Remember, it's low g of x, d high, f prime of x, minus high, f of x, d low, g prime of x, all over what? Low squared. Right. Okay, next up we've got chain rule. And this one's harder to know as a formula because you more just do it. This is the derivative of when you have a function with stuff inside it. So f of g of x is f of stuff. And the derivative of that is f prime of the stuff, so don't change g of x initially. And what do we multiply by? The derivative of stuff, right? So times g prime of x. Okay, so there's some general derivative rules. Some integral rules that are good to know. And again, there's more than just these. They're all listed on your formula cheat sheet that I handed out to you already. But here are some of the more useful ones on the AP. Most common is the integral of x to the n dx. Remember when you're writing integrals on the AP, remember your dx or dy or d whatevers. What happens if you're taking the antiderivative of the power rule? What happens to that exponent? It goes up 1, x to the n plus 1. Then you have to divide by n plus 1. And then don't forget plus c if there's no bounds. So this is just like x squared. You know when you go the antiderivative, that becomes x cubed over 3. That's what that's saying. There's some easy u sub ones that you can kind of get away with now using u sub. That's the integral of e to the kx dx, so k is a constant. What's the derivative of e to the x? Remember, the derivative of e to the x is just e to the x, so this would be e to the kx. And if I was taking the derivative, I'd multiply by k. So instead of multiplying by k, we divide by k plus c. Similar idea when you see the integral of a to the kx dx. So this would be like 2 to the 5x or 7 to the 8x. It's similar to the e to the x integral in that you still have a to the kx. But when you're taking the derivative of these, when it's not e, you multiply by ln of a. So now we divide by ln of a, but you'd also have to multiply by the derivative of kx. You'd have to multiply by k if you had the derivative. So we divide by that k, just like I did over here, plus c. So that one's not used as often, but it could come up. Recently, we did integration by parts. That's the integral of u dv, and that's equal to uv minus the integral of v du. You're all doing a nice job with that on the last test. What was the acronym we used to figure out what to make u? Lipit, logs, inverse trig, polynomial, trig. Oops. Just kidding. Misspelled lipit. Exponential, and then trig last. And that's when you have two variables multiplied by each other. Some other more recent ones. When you see the integral of 1 over 1 plus x squared dx, what's that? That's the tan inverse, or arctan, so tan inverse of x plus c. And similarly, the integral of 1 over radical 1 minus x squared dx, what's that? The radical one has the sine inverse of x plus c. Oops, sorry. And all of those, if I write let u squared equals something, those kind of questions, hopefully you remember what that means from just a couple weeks ago. You want this thing in the lower right to be a variable squared. So instead of letting u equal something with these, we let u squared equal whatever's over here. And the last integral rule I'm going to remind you of is that in the integral of 1 over u du, what's that? Can't use power rule because you'd have divided by 0 if you add 1 to the negative 1 power. So this is the ln of not u, but absolute value of u plus c. It's little nitpicky things like that you want to make sure you remember on the AP, or else they'll ding you for it. Okay. Got 3 examples, and then we'll get to some practice AP questions. This first example you'll probably see show up in a Barron's Review pretty soon, or one like it. Just so you know, this is in the Barron's Review, page 140. Let's say I'm given this information in a table. So here's x. I'm going to give you information about f of x, f prime of x, g of x, and g prime of x. And we'll have x being 1, 1, 4, 3, 2. The next row is 2, 4, 3, 2, 1. And the last one is 3, 2, 4, 1, 3. So there's just different values of all these functions for 3 values of x. And let's say I asked you to find the 2 of these. If I said if h of x is equal to f of g of x, find h prime of 1. Okay. Well, first off, we got to figure out what h prime of x is, and what rule are you going to have to use if I have f of g of x, f of stuff? It's chain rule. So first off, you should think, okay, h of x is f prime of stuff times the derivative of stuff. Now, if I specifically want h prime of 1, that would be f prime of g of 1 times g prime of 1. These are kind of fun to me, because then you have to start in here. What's g of 1? When x is 1, g of x is 3. So this is really f prime of 3 times g prime of 1. Okay, what's f prime of 3? When x is 3, f prime is 4. So this is 4 times g prime of 1. When x is 1, g prime is 2. 4 times 2, that answer is 8. Isn't that so fun? You can admit it because you're home alone. You don't have to look cool. One more. If h of x is f of x times g of x, I want you to find h prime of 2. Since these are so fun, if you want to pause the video and try this one on your own, be my guest. If you're ready to see my answer, here's what I did. What rule are you using if you're finding h prime? It's two functions multiplied, so you need the product rule. So h prime of x is the first times the derivative of the second plus the second times the derivative of the first. You want h prime of 2. So that would be f of 2 times g prime of 2 plus g of 2 times f prime of 2. Remember doing these earlier in the year? Well, we did them. Or you were supposed to at least. F of 2 is 4 times g prime of 2 is 1 plus g of 2 is 2 times f prime of 2 is 3. So we've got 4 times 1, 4, plus 2 times 3, 6, 4 plus 3, the answer's 10. Except f of 2. Okay, I think that's right. Let me double check real quick. It's different than what my notes say. Yep, I think that's all good. All right, so you should find some questions like that in the Barron's review assignments that I give you in a couple days, probably. Next thing I want to talk about is something that shows up every once in a while, and that's local linear approximation. And here's a question that would deal with that. If I said if f of 1 equals 1 and f prime of 1 equals negative 1/2, approximate f of 1.1 using the line tangent to f at x equals 1. So we did this earlier in the year. Basically what it means is I know f of 1 is 1, and I know the slope at that point is negative 1/2. So who knows what the graph looks like? It might look something like that, but we can use a tangent line, that blue line there, to approximate points nearby. Now, if I go all the way over here, the point on the blue line isn't that point to the point on the actual graph. But if I go close to 1, like 1.1 is, the point on the blue line would be almost the exact same as the point on the graph. You can't even see them in my picture. So that's why we can use a tangent line to approximate values of points nearby locally using a linear line. Okay. What you need to take away from this is when you see line tangent, immediately you should think, what's your goal? Y minus y1 equals m times x minus x1. Need a point in the slope. So I want it specifically at x equals 1. What's my point? Well, x is 1, and they tell you that y is also 1. What's your slope? Well, they told you that too. They told you f prime of 1 is negative 1/2. So slope's negative 1/2. So right away, I've got my tangent line. It's y minus 1 equals negative 1/2 times x minus 1. So now they want you to use that to approximate f of 1.1. So that's my x value. I'm going to plug that in here and use this line to get my y value. So 1.1 is near this point. I don't have an equation for f, but if I plug it into this tangent line, the blue line, it should be close to what the actual value would be on f. So y minus 1 equals negative 1/2 times 1.1 minus 1, which means I have y minus 1 equals negative 1/2 times 0.1. Okay, well, what's negative 1/2 times 0.1? What's half of 0.1? 0.05. This would be negative 0.05. So when I add the 1 over, 1 minus 0.05, we get that y is equal to 0.95. So our approximation is that f of 1.1 is about equal to 0.95. Okay, that's local linear approximation, and occasionally you'll see that come up. Okay. Last question before we get to some AP review. Let's do an integral. How about the integral from 0 to 1 of x squared plus 2x plus 6 all over x plus 1 dx? Looks innocent enough. It's not too crazy looking of a problem. What would you think to do? Maybe use u sub? If you thought that, that's not a bad thought. What do you think you'd let u equal? Well, you'd want u to be definitely the x squared piece. So then du over dx is 2x plus 2. I want x plus 1, so can you see how I get x plus 1 out of that? I divide by 2. So if I had, if I skip, can you see how du over 2 would be x plus 1 dx? Okay, is that good? That's my leftover piece? No, why is it not good? Because this needs to be in the denominator, and it's not over here. Not in denominator means this is bad. So u sub doesn't actually work. The trick here is, and it's something we don't do that often, rewrite with long division. We have done this before, but it hasn't come up in a long time. So what we could do is we could take x squared plus 2x plus 6 and actually divide it by x plus 1 to rewrite this, because that's what this means. So remember how to do that. What times x equals x squared? X times x equals x squared. So you multiply x by those, you get x squared plus x, and you subtract. Remember, we distribute a negative, so that becomes plus minus minus. So now this is just x plus 6. What times x will give you x plus 1. So multiply 1 times x plus 1, you get x plus 1. Subtract. You're left with 5. That's your remainder. Okay, so this is really x plus 1 plus 5 over x plus 1. Well, how does that help us? Okay, well, now I want the integral from 0 to 1 of x plus 1 plus 5 over x plus 1 dx. And that might not look better to you, but it actually is. Because these first two are really easy to take the antiderivative of. What's the antiderivative of x? X squared over 2. Plus the derivative of what will give you 1? X. Now 5 is just a constant, so we can leave that here. You can think of that getting pulled out front. If this was just 1 over x, what's the integral of 1 over x? It's ln of x, ln of the absolute value of x. If you let u equal x plus 1, what's the derivative of x plus 1? Just 1. So I can kind of get away without using u sub because there won't be any extra piece. But 1 over stuff becomes ln of the absolute value of stuff. Not plus c because we have bounds. So evaluate it from 0 to 1. Okay, so this would be 1/2 plus 1 plus 5 ln of 2. You can drop the absolute value when you know it's a positive. Minus, this is going to be 0, that's going to be 0. This will just be 5 ln of 1 when I plug 0 in. But what's ln of 1? Also 0, right? So this is 1/2 plus 1, that's 3/2, plus 5 ln of 2, which is fine. You could also say it's 3/2 plus ln of 2 to the 5th, or you could say 3/2 plus ln of 32. Any of those are fine. Okay, so I just wanted you to be aware that that long division does exist. I have seen it come up on the APs before. So just know that that's another strategy you can use if you can't figure out another way to take an integral. Okay, now let's do a couple practice APs. You should have, hopefully, these notes. The first one's from 2008. Notice what they're telling you. It says let g be a continuous function with g of 2 equals 5. So they give you a value of g. The graph of the piecewise linear function g prime, the derivative of g, is shown between -3 and 7. So this is g prime. This is one of those ones where I say g prime is equal to the graph. So those are the points that I'm looking at on the graph. How would g double prime be related to this graph? Well, if it's the derivative of this graph, what's the derivative mean? It's the slope of the graph. If I wanted to go back and find g, I'm taking the antiderivative. What's an integral of a graph mean? It's the area under that graph. So I always write this out first so I know what I'm looking at. Okay, part A. Find the x-coordinate of all points of inflection of the graph of y equals g of x between -3 and 7. Justify your answers. You all know how to find inflection points when you have an equation. Graphs screw people up. But these questions become easier if you think of them in terms of what you normally do. Normally, if you see a question about find all points of inflection, what do? You look for where the second derivative equals 0, or where else? Second derivative does not exist. Okay, so second derivative is slope. Is there any spots on this graph where the slope is 0? Nope, because there's no leveling off anywhere. Is there any points in this graph where the slope doesn't exist? Yeah, any corner. So x equals -1, 1, and 4. Now that's not enough to guarantee their inflection points. What else do you have to check for? Right, you got to check to make sure there's a sign change. So make a number line. Put -1, 1, and 4 on. Remember, this is a g double prime number line. So g double prime again is slope. So before -1, is the slope positive or negative? The graph's going up, so it's positive. After -1, it's also positive. It's still increasing, just at a different speed. So these are both positive, which means -1 is not a point of inflection. How about after 1? When the slope's negative, and after 4, it's positive. So what does that tell us? These two are points of inflection. So we could say point of inflection, and it's better not to abbreviate on the actual AP, but point of inflection at x equals 1 and x equals 4. Watch out for justify your answer. You have to say because what? You better not have said because it changes signs. You can't say it. Say because g double prime. And with a question like this, I would also write, which is equal to the slope of g prime, changes signs at those points. So there's your answer to part A. Okay. Part B, in my mind, is the hardest. Find the absolute maximum value between -3 and 7. Justify your answer. Where can absolute maxes occur? Could be critical points or endpoints. Now the endpoints are easy. We know the endpoints are -3 and 7. Where are the critical points? Well, the critical points of any graph are when the derivative equals 0 or does not exist. So in this case, the derivative is the graph. Where does the graph equal 0 or not exist? It will exist everywhere in between here. There's no open circles. It equals 0 at -1, 2, and 6, it looks like. We only care about maxes, so let's do a number line test with g prime this time on those critical values, -1, 2, and 6. And again, if I want to do positives or negatives and I'm looking at g prime, I'm looking at just the graph. Before -1, the graph's below the x-axis, so that's negative. After -1, it's positive. So this goes negative, positive. How about after 2? After 2, it becomes negative again. And after 6, right here, it's positive again. So -1 is a min. We don't care about that because I'm looking for the absolute max. 2 is a max. 6 is another min, so I don't care about that. Now again, that doesn't mean 2 is the max though, and that's the mistake that a lot of you make. I want the absolute max. It could be at 2, but it also could be at these endpoints. So the only way to know for sure is to check the original function because it wants the absolute max of g. It could be at -3, it could be at 2, or it could be at 7. Okay. Now, how do I evaluate these? Well, they did give us one information. They told us that g of 2 is 5. And that's a little handy. I know this is 5 right here. Now I got to find -3 and 7. Okay, now before x equals 2, the slope is sometimes positive and sometimes negative. And by slope, I mean the graph. So g prime is sometimes positive and sometimes negative. So I don't know if it's always increasing or always decreasing. Same with after 2. Sometimes g prime is negative, sometimes it's positive when I get to 7. So if I want to get information about g from g prime, I can take the integral from -3 to 2 of g prime of x, dx, because what will that equal? The original function, g of 2 minus g of -3. That's that fundamental theorem thing that keeps coming up. Now I use -3 obviously because that's what I want to find. Why'd I use 2? Because that's a value I know. So I know this is 5. I know this I want to find. And the integral of g prime, how would I get that from the graph? If I'm looking for stuff about g, I'm looking for the area. So the integral from -3 to 2 is all of this negative area plus all of this positive area. 2 triangles. So area of a triangle, 1/2 base times height. The base here is 1, 2. The height, it's going down, is -4. So this area is -4. How about this one? 1/2, what's the base this time? 1, 2, 3, times, what's the height? 1. So 1/2, 3 times 1, half of 3, 1.5. So it's -4 plus 1.5. That will give you -4 plus 1.5, -2.5. Okay, but I want to solve for g of negative 3. So if I add this over, I'll get that g of negative 3 equals 5 plus 2.5, which is 7.5. All of that to figure out what g of negative 3 is. Now what? I got to do that all over again to find 7. So think about how I do that. I take the integral from what to what? I use 2 again because you know it, up to 7 because you want it, of g prime of x dx. What should that equal? It should equal g of 7 minus g of 2. G of 7 we want. We know g of 2 is 5. We got to do some area analysis again. So from 2 to 7, now I'm going from here to here. So I've got this area plus that area. 1/2, what's the base? 1, 2, 3, 4. 4 times the height is negative 2. So it's going to end up being negative 4. This is 1/2. The base is 1. The height is 1. So that's just 1/2, or 0.5. So if I've got negative 4 plus 0.5, what's that? Negative 3.5. And when I add this 5 over, 5 minus 3.5 is 1.5. All that to say, your absolute maximum is at x equals negative 3. Now what they ask for? They want the absolute max value with a value of 7.5. That's what they really wanted, the value. And after all of that, you still have to justify. And what you would say is, because 7.5 is the highest value attained by G when evaluated at its endpoints and critical points. Okay, that was a lot of work for one part of the question, but that'd be worth a lot of points. Okay, last two parts. This is a really hard question. Find the average rate of change of g of x between negative 3 and 7. And here you want to find the average rate of change of g prime of x. Now, average rate of change, when you see those words, that's slope. And it's not the derivative, because it says average. So it's change in y over change in x. Rate of change is derivative. Instantaneous rate of change is f prime. Rate of change is just, average rate of change is just regular old slope. So the average rate of change of g, the slope on g between negative 3 and 7. This isn't going to be that bad. So average rate of change of g between negative 3 and 7. So here's the x values, negative 3 and 7. We did the work in the last part, 7.5 and 1.5. So change in y over change in x is 7.5 minus 1.5 all over negative 3 minus 7, which is going to be 5 over negative 10, so negative 1/2. Second. Just kidding, math is hard. This should have been 6 over negative 10, so negative 3/5. Sorry about that. Okay, and then part D, find the average rate of change of G prime on that same interval. Okay, that part's okay. So same steps. If I want values of G prime, where do I look? And just look at the graph, right? Because this is G prime. So it's -4 and 1. So do change in Y over change in X again. And you get -4 minus 1 all over -3 minus 7. So it's -5 over -10, which comes out to be 1/2. Now, if that wasn't enough, there's a second part to part D. Does the mean value theorem, well, we haven't gone over that yet, on that interval guarantee a value of C between -3 and 7 such that the derivative of G prime, G double prime, is equal to that average rate of change? Well, let's pull up the mean value theorem real quick. Okay, I went to my website and pulled up the notes. We're going to review all these theorems in a couple days. But here's what the mean value theorem says. If y equals f of x is continuous at every point over the closed interval, so is g prime continuous between -3 and 7? Yeah, it was continuous. There was no breaks. Good so far. And differentiable at every point on its interior. Okay, well, let's look again. Is g prime differentiable at every point? No, because there's corners. So right away, mean value theorem breaks down. So the question said, does the mean value theorem guarantee that value of C where the derivative equals the average rate of change? No. And it's because the conditions of the mean value theorem are not met. So no, because G prime is not differentiable at every point between -3 and 7. And then we're finally done. There was a lot in that question. It was a good one to go over because it's stuff that's going to come up. Hopefully when you run into questions that look like that on the AP and in the practice, you'll kind of have an idea of where to go now. So here's the great thing about not being in school right now. We're almost to 40 minutes. The period's almost over. But can you handle one more question? Sure you can. This one's easier, I promise. From the 2005 AP. Consider the curve given by y squared equals 2 plus xy. If you really can't handle being over 40 minutes, press pause, go get a drink, get a snack, then come back. Part A, show that dy over dx equals y over 2y minus x. Okay, so I've got the original equation. I want to find dy over dx. So what am I going to do? I'm going to find the derivative. And since it starts by looking like y squared equals 2 plus xy, how are you going to take that derivative? Implicit differentiation. So what's the derivative of y squared? 2y. Here's where you need dy dx equals, what's going to happen to 2? Goes away. And what do you have to remember to do with xy? There's the one trap. Right? It's product rule. So it's first times derivative of the second plus the second times the derivative of the first. We're supposed to show what dy dx equals. So get dy dx alone. So I'm going to move this over. 2y dy dx minus x dy dx equals y. Take that GCF of dy dx out, which leaves you with 2y minus x equals y. And divide. Dy dx equals y divided by 2y minus x. Hopefully that's what we were supposed to show. Yup, we showed it. Ease peas. Okay, part B. Find all points x, y on the curve where the line tangent to the curve has a slope of 1/2. Not a hard question if you can break down what it's asking. We want x and y points on the original graph. That's where you can easily lose a point. I'll show you why in a minute. The line tangent has a slope of 1/2. Slope means what in calculus? It means the derivative dy over dx equals 1/2. Okay, well I can do that. Set 1/2 equal to y over 2y minus x. Okay, let's try to solve this. So if I cross multiply, we get 2y, this is part B, 2y minus x equals 2y. Okay, now this is kind of weird. If you add the x over and subtract 2y, we get x equals 0. That was kind of handy. But that's not a point. That's the x coordinate where it happens. How do I get the y value on the curve? Well, don't plug 0 into this. That's just going to give you 1/2, the slope. If you want the y value, you got to plug 0 into the original. So now y squared equals 2 plus 0y, because I plugged 0 in for x right here, which means y squared equals 2. Take the square root. All points is another hint here. We have y equals plus or minus radical 2. So all points would be 0 radical 2 and 0 negative radical 2. There you go. That's part B. Part C says show that there are no points on the curve where the line tangent is horizontal. Kind of like part B, but if the line tangent to the curve is horizontal, what's that tell you about its slope? Well, horizontal slope means it's 0. So I need to do the same thing, but set dy dx equal to 0. So 0 equals that equation that we came up with in part A. What happens when you cross multiply this time? You get y equals 0, which seems fine so far. But we got to find the points. So we got the y value was 0. So go back to the original equation, y squared equals 2 plus xy. If I plug 0 in for y, I get 0 squared equals 2 plus x times 0. Uh-oh, 0 equals 2. No solution. So the reasoning here is for slope to equal 0, y must equal 0. But if y equals 0, x does not exist. We just showed that there are no points with a horizontal tangent. Now this just said show. It didn't explain. So could you have gotten away without writing this? Maybe. But again, they're really picky on the AP. So if you can kind of explain your reasoning always, and if you've got the time, I would write that. Okay, almost done. Let x and y be functions of time t that are related by this equation. At time t equals 5, the value of y is 3, and dy dt is 6. Find the value of dx dt at that time. So this is kind of a related rates type question. If they're giving you dy dt and dx dt, they want you to take this derivative with respect to t. So that's what we got to do. So again, we've got y squared equals 2 plus xy, and I'm taking the derivative with respect to t. So again, the derivative of y squared becomes 2y, but now it's dy dt, the derivative with respect to t. 2 still goes away, and I still got to use product rule in this part. So first times the derivative of the second with respect to t, plus the second times the derivative of the first with respect to t. Now I think they give us most information. They tell us that when t is 5, y is 3, and dy dt is 6. So this is 2 times 3 times 6, y is 3, dy dt is 6, equals, do I have x? No, and I want to find dx dt. Any idea how I could find x? We're going to leave that blank for now. We know this is 6. We know y again is 3. I'm looking for dx dt. So how I find x is using this original equation again. We know that y is 3. So 3 squared equals 2 plus x times 3. 9 equals 2 plus 3x. Subtract. 7 equals 3x. Kind of annoying, can't get a nice number. X is 7/3. But it actually doesn't come out so bad because we've got a times 6 here. So this is 6 times 6. We got 36 equals, if you cancel that, this is a 2 now. So that's just 14 plus 3 times dx dt. Subtract the 14, you get 22 equals 3 times dx dt. Finally, when you divide by 3, 22/3 equals dx dt. There you go. All right, so this last one wasn't as bad, I don't think, but you can still see there's little tricks that you have to know, and that's why it's so important that you watch these videos and see what tricks the AP throws in, because the more you see, the more that you'll start to recognize them. All right, sorry for going a little bit long. That's all I've got. Good luck.